So, good morning, students. Welcome in next lecture of Math of 242 Operation Research. Presently, we are studying second chapter queuing system or queuing theory. In last class, I have started the birth and death process, and I have derived the governing differential difference equation or Chapman-Kolmogorov differential difference equation. From that, we have derived or formulated the steady state system of linear equation. Thereafter, we have solved, and one question we have this question we have solved in last class. So it is a similar type of the question. You can note down this question. It is coming. It come in the recording. Right. Suppose that service station arrival pattern is in Poisson fashion, and the service time is in exponentially distributed. It is given to you both arrival and inter-arrival time and service time. This service time and the inter-arrival time. If the arrival pattern follow the Poisson fashion, this implies that inter-arrival time follow the exponential distribution. Right? It follow the exponential distribution. The arrival and service rates are given by, here it is the lambda n and mu n. So this denote that we have the state dependent arrival rate and state dependent service rate. And here we have find all the steady state probability for this system, find mean number of customers in the system, what is the effective rate of service of the service station. So it is given to you. Here we have the system. Initially there is no customer, zero customer. We denote the state by the node. Then first customer arrive with the rate lambda 1, then second customer arrive with the rate lambda 2, then third one lambda 1, then third one with the lambda 2, right, then fourth one with the lambda 3. And first customer get the service with the rate mu 1, two customers get the service with the rate mu 2, right, with the rate mu 3, and here we have the rate mu 4. And it is given to you lambda n is 12 minus n. So this will become it is the 12 minus 0, 12 minus 1, 12 minus 2, and 12 minus 3. After that all are the 0, right? After that all are the 0, so need not to make the notes. Then after, here we have the n by 4 plus 8, so it will become, and n is equal to 1 2 3, so 8, and it is the 8 plus 1 by 4, it is the 8 plus 2 by 4, it is the 8 plus 3 by 4, and this is the 8 plus 4 by 4, right? So here we have, so from here if you compute the c naught is what, always 1, then c1 is lambda naught upon mu 1, so this is the 12 upon 33 by 4, and c2 it is the lambda naught lambda 1 upon mu 1 mu 2, so it is 12 into 11 upon 33 by 4 into 34 by 4, and c3 it is the lambda naught lambda 1 lambda 2 upon mu 1 mu 2 mu 3, so this is the 12 11 10 upon 33 by 4, 34 by 4, and 35 by 4. Similarly, C4, C4 will come lambda naught, lambda 1, lambda 2, lambda 3 upon mu 1, mu 2, mu 3, mu 4. So 12, 11, 10, 9 upon 33 by 4, 35 by 4, no, 33, 34. Sometimes it is very hard to write on the tab. 34, 35 by 4, and then we have here, so it is the 9. It is 9. So 9 and 9 cancel out. So here we have 48 upon 33, right? So have you calculated this? This is a 3 times 16. Anyone? This only?
Yes, sir.
Set 10128 256. 256 upon it is 17. This only? Please check the calculation. This is also the same thing. So here we have the C0, C1, C2, C3, C4. Please check that, because if it is the wrong, then complete answer will be the wrong. And we know that from the normalizing condition, and from here also you write the Cn is equal to 0 for n greater than 4, because the lambda 4 is equal to 0. Lambda 4 is equal to 0. So here we write the Cn is equal to 0. This is a very necessary line to write. So from here we know that summation of Pn, n where n from 0 to infinity is equal to 1, that is the normalizing condition. That is the P naught, P1, P2, P3, right, P4, and so on. So this is P naught. If you take common, so here we have the 1 plus C1 plus C1. It is the P naught 1 plus C1 plus C2 plus C3, right, plus C4, and so on. So this is the P naught 1 plus C1 we have computed as 48 by 33, 48 by 33. Then after we have the 96 upon 51, 96 upon 51. Then after we have the 256 upon 119, 256 upon 119 plus 256 upon 119. So this is your P naught is equal to 1. So P naught will be the inverse of this. Anyone can give the answer? So after having the P naught, we can compute the P1, P2, P3, P4, right? Or instead of the P4, you write the Pn, that is equal to 0 for all n greater than 4. So this is the necessary line to write. So here we have to compute the all necessary probabilities. After computing the P naught, we can compute P naught, P1, P2, P3. So P4 also, P5 I think. Just wait a bit. What is the last node? Last node is P4. So it is the P5. So we can compute the P1, P2, P3, and P4. Here we have the mm, Pn, n greater than 5, n greater than 5. That is equal to 0. So after having this, if you have to compute the L is what? Basic formula is n into Pn, n vary from 0 to infinity. That is the 1 into P1. We know the value of the P1. 2 into P2, 3 into P3, 4 into P4. So that is the L. Then we compute the lambda var. So lambda var is what? N is equal to 0 to infinity lambda n into Pn. That is the lambda 0 P0 plus lambda 1 P1 plus lambda 2 P2 plus lambda 3 P3, and rest are 0. So it is the 12 P naught plus 11 P1 plus 10 P2 plus 9 P3. So whatever the value you have, you can write. Then we have to compute the effective service rate. So for the steady state, you know mu var is equal to lambda var. So whatever the value we have, that we can write here. Is there any doubt to write or to compute any state probability? So these three things we have to compute here. Here, please always leave the question in the fraction only. Never please write in the decimal. Sometimes we have the 1 by 3, so that will create the problem in the later part. So please always keep the solution in the fraction form. Let us have this question. This is from your book. In a single server queuing system with Poisson input and exponential service time, arrival tend to get decreased when more customers more more customers are present in the system. Specifically, assume lambda n is equal to 2 upon n plus 1 and mu n is equal to 3. It is given to you that when we have the more customer, there is a more chance of discouragement. Means the customer shows the impatience in joining the system. If there are a long queue, it is a common behavior, it is a common impatience behavior of the customer that they show the discouragement in showing. So discouragement means the arrival rate is decreasing, and the function of arrival rate is given here as a lambda n is equal to 2 upon n plus 1 and mu n is equal to 3. Find the steady state probability distribution of the system. Find the L and W. So what is given to you? Initially we have 0 customer, 1 customer, 2 customer, 3 customer, right? N minus 1 customer, n customers, and n plus 1 customer. Initial rate is the lambda 0. So when we put n is equal to 0, it will give the 2. Then it is the 1, and then it is the 2 by 3, then it is the 2 by 4. So you can see it is decreasing, and here we have the 2 upon n minus 1 plus n plus 1, so 2 upon n, and here we have the 2 upon n plus 2 upon n plus 1, and so on. And service is given to you as a 3. Service is given to you as a 3, 3, and here we have the, for all n, it is given to you as a 3. So now you have to compute the value of all steady state probabilities. Find the steady state probability distribution. So in the same fashion, we have to move. So in this case, we know that Pn is equal to what? Pn is equal to Cn into P naught, where Cn is lambda naught, lambda 1, lambda 2, and lambda n minus 1 upon mu 1, mu 2, and mu n. This is the Cn. So what is the lambda? It is the 2 by 1, it is 2 by 2, it is 2 by 3, it is 2 by n. For the lambda n minus 1, it is the 2 by n upon mu 1, mu 2, mu 3. So 3, 3, 3, 3. So you can write it as a 2 by 3 power n upon 1 into 2 into 3 into n. So that can be written as 2 by 3 power n upon factorial n. That is your Cn. Now we know that from the normalizing condition, from normalizing condition, what we have normalizing condition, sum of all probability Pn is equal to 1, n is equal to 0 to infinity. So summation n is equal to 0 to infinity, it is the 2 by 3 to power n upon factorial n. It is equal to 1. Can you say about something about the left hand side? It must equal to anyone? Anyone? Into P naught. Into P naught also. Anyone, please tell me what will be the left hand side? Are you getting my voice? Nobody is
Sir, is
replying.
it e raised to power x with x equals to 2
E
by
to
3?
yes, yes. It is the e to power 2 by 3 P naught 1. So P naught will come here e to power minus 2 by 3. So from here the Pn will come. Pn will come 2 by 3 power n upon factorial n e to power 2 by 3. E to power minus 2 by 3. E to power, yes, e to power minus 2 by 3. That is your Pn. For n is equal to 0, 1, 2, and so on. From here, you can recognize something. From the expression, you can recognize something. It is a very famous expression.
Poisson distribution.
Yes, it is the PDF of the Poisson distribution. It means you can say that it follow the Poisson distribution with parameter 2 by 3. Right? E to power minus lambda, lambda to power n upon factorial n. So it follow the Poisson distribution with parameter 2 by 3. Clear? So here we have computed the all steady state probabilities. Thereafter, we have to compute the L. So L, we know that for the Poisson distribution, average is mean number of customer or average, right? That is the lambda. if you say it is the lambda, or instead of the lambda you take another variable. Lambda generally we denote for the arrival. Let's say gamma. So L is what? Summation of npn. Summation of npn. So npn, n vary from 0 to infinity. So we know that it is the whatever the parameter gamma. For the Poisson distribution, we know how to drive the mean. So I'm not going in that part. So it is the 2 by 3. Then after we have to compute the, in the question we have to compute the w, right? So w by the little formula, w by the little formula is what? W is equal to L upon lambda bar, where lambda bar is what? Effective arrival rate. Effective arrival rate. And it is equal to summation lambda n into pn, n vary from 0 to infinity. So this summation n is equal to 0 to infinity lambda n is given to you as a 2 by 3 power n upon factorial n into p naught, or e to power minus 2 by 3. So from here, if you see here, so this is the basic formula we have written. So here we have the, this is the lambda n 2 upon n plus 1, 2 by 3 to power n upon factorial n into e to power minus 2 by 3. So from here, if you multiply both side by the 3, so numerator will become this 2, and this 2 will form the 2 to power n plus 1, and you multiply and divide by the 3. So here we have the 2 to power 2 upon 3 to power n plus 1, and this n plus 1 into factorial n will give you the factorial of n plus 1, right? Factorial of n plus 1. And this is the constant. This is the constant e to power minus 2 by 3. So that we have written here. So for this, any doubt? So again, this is the exponential series, right? That can be written as e to power 2 by 3 minus 1, right? E to power 2 by 3 minus 1. So if you just multiply this inside, e to power minus 2 by 3 inside, so here we have 3 into 1 minus e to power minus 2 by 3. And we know that by little formula w is equal to L upon lambda bar. So it will become the 2 by 3 upon, right? 2 by 3 upon 3, 1 minus e to power minus 2 by 3. That is your w. Now, anything you want to ask here? Now, uh, presently we are studying the Poisson cube. So we have the following 6 standard Poisson cube in our course. We have the more Poisson cube also, but in your course we have the following 6 Poisson cube. So we start from the, right? We will start from the this infinity. Infinity is also known as the self-service model. What is the self-service? Anywhere you noted the self-service model? Self-service. This word
In buffets,
in
like
what you have
when
said?
in buffets we have to take food on our
In
own.
buffet, in cafeteria, in iska, means in the this idli tot. Everywhere we have the self-service system. So in the self-service, customer itself is the server. Customer itself is the server. Means in this case, initially we have the 0 customer, then 1 customer, then 2 customer, 3 customer, 4 customer, n minus 1 customer, n customer, n plus 1 customer. In this, here we have the assumptions that the customer join the system with the following the Poisson process. Customer join the system following the Poisson process means inter arrival time follow the exponential distribution with parameter lambda. With parameter here lambda, with parameter lambda, with parameter lambda. In the Poisson Q, we know that inter arrival time follow the exponential distribution, as well as the service time also follow the exponential distribution with rate mu. If there is one customer, it means there is one server. That customer himself is the server. So when there is one customer implies that there is one server, and that server will provide the service with the rate mu. If there are two customers, it implies that we have the two servers, so that the service rate will become the 2 mu. Because for the you know that the additive property of the Poisson distribution, right? So here we add the rate. In the theorem also I have told you, when we have the homogeneous system, then when we have the n servers, then the service rate will be the n mu. If we have n servers, then the service rate will become the n mu. So presently we have the two customers implies the two servers. So here the service rate will become the 2 mu. Similarly here we have the 3 mu, here we have the 4 mu, here we have the n mu, here we have the n plus 1 mu. And that is the self-service model. That is the state transition diagram. This is the state transition diagram, right? State transition diagram of self-service model. Self-service model. In what is the candle notation of the self-service model? Have you noted? It is the M M N FCFS infinity infinity. This is the candle notation of the self-service model. What it implies? Infinite population. What it implies? Infinite capacity, service discipline. Service discipline is the first come first serve. Number of servers. So number of server, it is exactly whatever the state of the system, n state of the system, that is the number of the server. Service time follow the exponential distribution with parameter mu. Inter arrival time follow the exponential distribution with parameter lambda. That is the self-service model. Sometimes we write this Condell notation as mm infinity, FCFS infinity infinity. Both are the same thing. Either you write the mmn or infinity. Both represent the self-service model. Self-service model. So if you want to write its governing transient state equation or Chapman-Kolmogorov differential difference equation, so I have told you from the state diagram we can write easily. So whatever the outgoing arrow, that will come with the negative, and whatever the incoming, that will come with the positive. So if you have to write for the zeroth node, so for the zeroth node we have the equation dp0 by dt is equal to minus negative plus positive from the for the incoming. Positive for the incoming. Then for the nth node, if you want to write the equation for the nth node, why we are writing the nth node? You see any node, every node has the same type of the characteristic. So if you write for the nth node, so here the outgoing is the lambda and n mu. So here we write minus lambda plus n mu p n t plus what are the incoming? Incoming is here, incoming is lambda and the n plus 1 mu. Lambda from n minus 1 and n plus 1 mu from the n plus 1th node, for n is equal to 1, 2, 3, 4 and so on. With initial condition p0 0 is equal to 1 and pn 0 is equal to 0 for n is equal to 1, 2, 3 and so on. So we have the Chapman-Kolmogorov differential difference equation or transient equation. From here we can write the steady state equation. So minus lambda p0 plus mu p1 is equal to 0 and minus lambda plus n mu, lambda plus n mu pn plus lambda pn minus 1 plus n plus 1 mu pn plus 1 is equal to 0 for n is equal to 1, 2, 3 and so on. With normalizing condition summation n is equal to 0 to infinity pn is equal to 1. So this is the steady state system of equation for the self service model. Now you can apply the birth and death process here, whatever the process there we have applied, right? So from there we know that what is the solution? Solution is Pn is equal to Cn into P naught, where Cn is what? Cn is lambda naught, lambda 1, lambda n minus 1 upon mu 1, mu 2, mu n. And lambda, all the lambdas are given to you as a lambda, lambda and lambda. It means for the self service model, what is the condition? Condition is for the self service model, condition is lambda n is equal to lambda for n is equal to 0. Always we have to start from the 0, right? For 0, 1, 2 and so on. And what is the mu n? Mu n is given to you as a n mu for n is equal to 1, 2 and 1, 2, 3 and so on. So here this is the rate condition for the self service model. This you have to remember. For the self service model we have the lambda n is equal to lambda and mu n is equal to n mu. So here mu1 is what? Mu1 is mu, mu2 is what? 2 mu, mu n is what? N mu. If you write the lambda upon mu power n, so in denominator we have the 1 into 2 into n, which can be written as lambda upon mu power n upon factorial n. And this can be written as rho to power n upon factorial n, where rho is equal to lambda upon mu, lambda upon mu, that is our Cn. So Pn will become rho to power n upon factorial n into P naught by the normalizing condition. By normalizing condition By normalizing condition, sum of all probability is equal to 1, that is from 0 to infinity, or P naught, P1, P2, and so on. So from all P naught we can take common. So here we have the 1 plus rho by factorial 1 square upon factorial 2 plus rho cube upon factorial 3 plus rho to power n upon factorial n plus and so on. That is our the sum of e to power rho. E to power rho, and so from here P naught will come e to power e, that is our P naught. From here the Pn will come rho to power n upon factorial n e to power minus rho 3 and so on, for n is equal to 1 to 3 and so on. So here you can say that it follow the Poisson distribution with parameter rho. So from here n, n is state of the probability, state of the system, state of the system, state of the system follow the Poisson distribution with parameter rho. State of the system follow the right state of the system follow the Poisson distribution with parameter rho. That is our self-service model. In general, we call it as a model 6. This is the model 6. Model 1 we will do later on, but this is the model 6. So MMN FCFS infinity infinity, or MM infinity FCFS infinity infinity. This model, in this model, arrivals are in the Poisson process with mean rate lambda. That is this M. That is this M. The service time are independent exponentially distributed random variable, each with parameter mu. That is this M. The number of server is infinite. Number of server is infinite, or whatever the number of customer in the system. So for example, self-service situation where each arriving customer serve himself. If at a time the number of customer nt is equal to n, at time t there are n servers in the system, hence mu n will become the n mu for all n. So main thing here, the condition you have to remember, lambda n is equal to lambda and mu n is equal to n mu for all n. This n start from the n is equal to 1, 2, 3 and so on, and this n start from the n is equal to 0, 1, 2, 3 and so on. Arrival always start from the 0 and mu always start from the 1. So here we have written the same thing. So from here we have computed the Cn. Need not to go for the steady state equation or transient state equation. Directly from the birth and death process, we know the solution Pn is equal to Cn into P naught, where Cn is equal to lambda naught, lambda 1, lambda 2, lambda n minus 1 upon mu 1, mu 2, mu n. So if you put the value, you will get the required steady state probabilities for all n. Now, now we have to compute the value of the right L. So what is the L? What is the L? L, it is the expected number of customers in the system. Expected number of customer in the system. We know the basic formula. It is the summation n is equal to 0 to infinity n into Pn, which can be written as P1 plus 2P2 plus 3P3 plus 4P4 plus npn plus and so on. So it is the p1 is the c1 p naught, c1 p naught, 2 c2 p naught plus n cn p naught. So if you take the p naught common, inside we have the c1. c1 or cn we have computed as cn we have computed as this is your cn. Cn is what? Row to power n upon factorial n. So c1 is the row. C1 is the row. It is the 2 row square upon factorial 2. It is 3 row cube upon factorial 3 and n row to power n upon factorial n and so on. So 2, 1, 2 is cancelled out. Here we have the factorial 1, 3, it will give you factorial 2. This, it will give you factorial n minus 1. So if in the numerator, if you take the row common, row into p naught. So inside we have 1 plus row upon factorial 1, row square upon factorial 2, row to power n minus 1 upon factorial n minus 1 and so on. So now the bracket is what? Now the bracket is what? Row p naught e to power row, e to power row, and p naught we have already computed as p naught already we have computed as p naught is the e to power minus row. So just you put the row e to power minus row, right, and e to power row. So this will give you row. That is the L is equal to row for the self-service model. Expected number of the customer in the system will be the row. Directly you can write, since the state of the system follow the Poisson distribution, so from there also you can write its L. But here we have derived, right? Otherwise we know that mean of the Poisson distribution is equal to the parameter. So from there also you can write. So this is your L. So L is equal to, here we have the row. Then after, since each customer is served as soon as he arrives, so there is no chance of the queue. In this case, for self-service model, there is no queue. There is no queue. If there is no queue, it means number of customer in queue is equal to 0. Number of customer in queue is equal to 0, and we know that n is equal to q plus u. Q plus u, where u is what? Number of customers in service, number of customer in service, right? So if you take the expectation on both sides, so here we have the q plus u. Since there is no q in the self-service model, it is 0, so it is equal to eu. So what is the meaning of the eu? Eu or en, right, or en, that is equal to row. It means here we have the here it will give you expected number of customers, in service. Expected number of customer in service means in the self-service model every customer is in service, right, or in every customer is in service. So that's why we have the same expectation. And here row is what? It is the lambda upon mu. This rho is also known as the utilization factor. Utilization factor. Utilization factor. So here we have written the En is equal to uh, right EU also. So that is one more formula, right? So LQ we have computed. LQ is what? It is the EQ. EQ, since Q is equal to 0, so this is always 0. This is always 0. And we know that lambda var is what? Summation of lambda n into Pn for n is equal to 0 to infinity. All the lambdas, all the lambdas are lambda. It is given to you for the self-service model. For the self-service model, I have written somewhere, for the self-service model, all the lambdas are lambda. So here, if you put this value, so this will become n is equal to 0 to infinity lambda into Pn. This can be written as lambda n is equal to 0 to infinity Pn. And what is this? What is this summation Pn? Anyone, please? It is equal to, yes, it is equal to 1. So it will become the lambda. So here the lambda var is equal to lambda. Effective arrival rate is equal to lambda because there is no loss. The customer who is joining will get the right. The customer who want to get the service will join there. There is no losses. After that, we know that little formula L is equal to LQ plus lambda var upon mu. L is what? Rho. It is 0. It is lambda upon mu. So we have the rho is equal to rho. It means it verify the little formula also. It verify the little formula also, right? And what is the W? It is the E of T, that is the expected waiting time. Expected waiting time. Expected waiting time. And by little formula, it is the L upon lambda. L upon lambda. So L upon lambda means rho upon lambda, or lambda upon mu upon lambda, or you can say 1 upon mu. So how much you have to wait? It is what? It is the mean service time, right? It is the mean service time. It is the mean service time. So how much you have to wait? Expected waiting time. Expected waiting time is equal to mean service time. Whatever the average service time of the system, that much you have to wait, because you have to wait for your service only, because it is the self-service model. So you have to wait until unless you have not completed your service. So it is the, you have to wait for the mean service time, right? For the mean service time. So here we have the W is equal to 1 upon mu. Since there is no Q, so WQ is what? WQ is the E of TQ. There is no Q, so it is equal to 0. It is equal to 0. And from here, we know that W is equal, little formula, one more little formula we have, W is equal to WQ plus 1 upon mu. So you can say that this W is what? 1 upon mu. It is 0 plus 1 upon mu. 1 upon mu. So it is verifying the little formula also. So that is the few things about the self-service model, right? So we have computed the En. EU is equal to rho. Since there is no customer in the queue, so LQ and WQ is equal to 0, that I have explained. Then lambda var is equal to lambda var is equal to lambda. Effective arrival rate is equal to the arrival rate. So here mean average service time is equal to expected service time, that is the W is equal to 1 upon mu, right? So that we have derived here. So question we will do in next class. So all the derivation part we have completed. Question we will do in next class.
So just one thing.
Yes, yes, please.
So
I have not
in the
read the comment. Yes, please ask.
yes, so in the self-service queues, so the cases where there is actually just a limited number. Suppose in the same buffet wala example, so it is following a self-service system. But what if the number of counters from which you can get food is just three? So it is still essentially is it considered as there are only three servers in
So
that way? It's
it is
considered?
up your assumption. Na? If you are considering that counter as a server, then it is the MM3 model. It is up to you, no, how you are assuming your system. If it is the self means, for example, you want to take the bath in the Ganga river, go and take bath. It is the totally self service. But in the restaurant, if you are depending over the counters limit, then it is the finite server, three counters, four counters.
Yes,
So that
but
is
then
another model then.
the thing is we are the number of counters are limited, but the server is the person, the customer himself only, right? So it is still self-service, but like finite service. So how will that be modeled?
Actually, in that we have the different. In that we have the different modeling that will not come under the self service. Completely self service. It is a mix of the self service plus limited service facility.
Okay, sir.
We have the
So
we have more the models. So you just wait for that.
okay, sir. Right.
We have the total six models. No, presently I have covered the easiest model. So
Okay, sir.
one by one I will cover all the models.
Okay, sir. Thank you.
Yes. Roy, what you have asked?